So yeah, we'll kick this session right off. In person here, we have Patrick Aleo here to talk of well, about astronomy. Let me your keynote, right? Yeah, yeah, let's be a keynote there. And you should just be able to play there too. Okay, cool.
Perfect. Thank you to the ATDS organizers for having me speak. So I'm a six-year astronomy PhD candidate at the University of Illinois at Urbana-Champaign, and I am actively and deep in the transition process, as you've heard about in the earlier speakers, applying for these data scientist type roles. And I'll have a few of some brief comments towards the end, just based on my experience, and happy to answer any questions throughout today or going forward about these kinds of things. But I would like to talk to you a little bit about kind of the big data and machine learning anomaly detection work that I do in my current research, and some of those like big scale industry type applications and models that I use in my research, which kind of help me bridge the gap for a lot of these applications that I'm sending out currently. So if it's too astronomy specific, I'm sorry, but hopefully I can focus on a lot of the interesting questions that you have for the data science transition, what that means as a current PhD student looking. So I work a lot in the time domain sky, which is just objects that change in brightness as a function of time. And you have many different types of objects in the night sky, variable stars and quasi-stellar stuff and AGN and supernovae. And I work in the supernova regime. But with all of these types of objects, you take a measurement of the brightness function of time. You call them light curves. These light curves are, very gappy. There's lots of irregularities to them. Their errors are heteroscedastic, and you need kind of a uniform way to treat these data so that you can apply a lot of your, big data models for these data. So one way that astronomers treat this is you measure the statistical features. So you're measuring the period or the amplitude of these kinds of light curves, and you can call them kind of feature vectors in some larger parameter space. It's just a way to homogenize all of your irregular data and treat them in the same manner. And as you can imagine, you can get a little stir crazy and throw every statistical test that you can at these kinds of light curves, and you end up with some huge data set. Some features are more useful than others, and a lot of this feature engineering work that you do in the data science and their applications is to.
We lost the beats for a sec. So
okay. Yeah.
Pardon me, the online people lost the talk. Let's see, where Zoom go? This is not what I want. Ah, wait, there it is. Okay. Okay, that looks more like what we were expecting. Now go away so I can hit play. Well, eventually it'll go away. There we go. Sorry about that.
But as just was saying, a lot of those feature engineering work that you'd use in data science to try to parse out what are the most interesting and relevant features to use comes into play here. And as I mentioned before, I work in supernovae, and they have, a very diverse taxonomy. And some of these objects are more rare than others. Some of them come from rare environments or just progenitor systems that we don't really know exist. And we're building up these statistical samples of a lot of these rare supernova classes, and getting observations and follow-up of their spectroscopy to better understand the supernova themselves, the explosion scenarios, their local environments, and the native populations of a lot of these supernovae. And supernova don't come in a vacuum. They come, from host galaxies somewhere, and there's been a lot of good work that associates, supernovae to their host galaxies, and we know that there's a correlation between the host galaxy and the supernova themselves. Some of these supernova that are come from older star populations like white dwarfs. A lot of the thermonuclear type 1a supernova tend to come from these more evolved, older elliptical galaxies, and these core collapse supernovae tend to come from, younger star populations and late type galaxies or spiral type galaxies. There's been a lot of really great work that is just trying to use the contextual information alone to better study and classify these supernovae. So my goal for this particular project is to try and find these broad classes of anomalies, so spectroscopic anomalies, supernovae that don't fall nicely into the type 1a and type 2 normal classes, which in a broad magnitude limited survey, those will count for about 90% of all the objects that you observe. So I'm looking for that like 10%. I'm also looking for objects that are contextual anomalies, so supernovae that appear in a non-typical environment based on what we know about their host galaxy correlations, and then behavioral anomalies, so supernovae that have some process-driven interaction with a local CSM, or there's some like weird behavior. We want to know about that. We want to be able to flag them as early time and as low latency as possible with high purity, because in these era of large time domain surveys, we have very few we have limited resources to get follow-up spectroscopy, which is our best way to best understand their local environment. The data set that I use comes from this Wiki Transient facility. It's a northern sky survey that observes the night sky in G and R bands and comes about every 2 nights. And the systems that process these are called brokers or time domain brokers. All the ones are kind of listed here: Alerce, Lacer, Fink, Antares, and a couple others. I use the Antares broker, but basically what they do is that they ingest the nightly data that comes from the Zwicky Transit facility. They host them in a big database and make it accessible for scientists like us who want to do the work that we need to do. And the great thing about a lot of these broker systems is that they provide development landscapes for us to use their data that they host from the Zwicky Transit facility, develop our models, deploy our models, so that our models are actually running on real time in the data streams, which is a great thing. And one of the most applicable parts of being a data scientist is, having that model deployment experience and actually having your models do something with real data. So that's what I did. I wrote basically is just a piece of Python code called a filter that I was able to train some algorithms on. And the nice thing about having a system in deployment, and I'm happy to talk more about that if you have questions on it, is that at least in the landscape of this, if an object passes all of my selection cuts and passes, with a high anomaly detection score for my model, it gets tagged to the local object, and it also, the sign score and everything that gets tagged with the object that we can, look for later on. And an example of this blue vertical line is when my anomaly detection algorithm flagged it as, hey, this is probably anomalous. And purple is when we actually got the follow-up confirmation that yes, that this object is in fact a type 1b, which is a stripped envelope supernova. It's going to fall in my definition of spectroscopic anomaly, that this is anomalous, and so that's a bona fide anomaly. And I won't have time to get into any real little bits of the entire process, but I want to talk about 2 of my main functions or directives of this project, which one is the anomaly detection, and then the secondary one is an approximate similarity search. And I will get to that more later because that uses a lot of these big data applications as well. Basically, I had this 120 dimensional feature vector. So all these 120 dimensional features, half of them were Likert features, and the other half were features of the host galaxy themselves. And if you just go on the spectroscopic label alone, I'm able to train a random forest classifier model to identify these spectroscopic anomalies, so anything that's not type 1a or type 2, with about 50% purity, which is not bad, especially because this is a very imbalanced data set. As I said, I'm looking for like the 10% of objects that don't fall neatly into one of these broad 1a or type 2 normal categories. But as I was saying before, we want to also consider the contextual anomalies, behavioral anomalies, and sometimes the spectroscopic labels are wrong that, that gets uploaded from TNS. Sometimes that they're outdated, or, there's there's some codes that people use for classification, and sometimes there's a bit of debate as to which object falls where. And so just to give you a sense, so this is the example of a spectroscopic anomaly I was talking to you about, where on the left here is a tidal disruption event, which is where a star gets too close to a black hole and gets shredded. And on the right is envelope supernovae, the blue verticals, where my anomaly detection algorithm flagged it as, like, if you look on the right-hand plot here, and it flagged it a week earlier than when there was the first spectroscopic confirmation of this. And so we're trying to push for these boundaries of early and earlier spectroscopic classification to better understand a lot of these local environments. The algorithm is also great for picking out these behavioral anomalies. So a supernovae that seem to have this secondary bump caused by interaction with their local CSM. And these are interesting. This is a smaller rare subclass of objects, and we want to know more about how there is a local CSM in the first place, and what does that interaction do to the light curve and the spectra themselves, and what can you tell about the exposure progenitor. And there's also these contextual anomalies, so some like blue transient that may or may not be from this elliptical, or might be from some far faint away thing that you can't really see. In any case, this was one that was interesting, but it was missed in real time. But when you consider kind of all these together, and you tune your hyperparameters for identifying a lot of these different anomalies, we can actually get a very high purity score, almost 90%, which is kind of the directive, we want whenever algorithm says, hey, this is interesting, that we look at it and that we get follow-up of it. So yes, our completeness, we are missing, 60% of all the anomalies considered, but we rather miss a few than waste our resources, especially in these coming surveys where we're just going to have a deluge of objects, and we need to be very judicious with our resources. Going back a bit to how this actually works. So this model is deployed within the Centauri's broker system. I've connected up a Slack bot so that it basically talks with the Centauri software infrastructure, and it pulls the new objects per night that has a tagged anomaly score of greater than 50%, or any threshold that I choose a night. And then I take those objects, and then I ask my collaborators, hey, can you get spectra of these objects for the ones that don't currently have spectra to them? And the one I'm showing here is a tidal disruption event that my algorithm flagged, for anybody else, and was able to get spectra and the follow-up confirmation. So that's, a great application of that. But also what I wanted to do, because I have such a big data set, was use something from industry. This is called Anomaly. It's what Spotify uses for song recommendations. And I'm using it here for supernova science, which is really cool and pretty applicable. And it's nice and easy to talk about in my applications, because it's something that people understand. Oh, Spotify song recommendations. Yeah, like I understand that. I won't, it's sometimes a bit harder to talk about a lot of the unique science that you do because it's so jargon heavy. Anyway, this is an approximate similarity search method, so it's not going to find your exact nearest neighbor, but it's going to find a pretty close one with a lot of time saved. And so I'm looking for similar supernova and host galaxy environments together to look for nearest neighbor pairs. So in this case, the reference here that I'm using is this type 1a at a redshift 0.04. And I am, just to be clear, I'm not using the redshift class or the redshift or the classification label at all in my similarity search. I'm just using the raw feature, the statistical features from the light curve and the features that I derive from the host galaxy environment and those associations. And, I find nearest neighbor pairs, and you can see that all the matches are really strong. They have very similar evolutions. They have in both the light curve and host galaxy space. So this is great. It's an easy way to, within a large data set of, thousands and thousands of samples, to find really quickly objects that are very similar to the ones of interest. This is great for example here, where your main reference object doesn't have many observations post-peak, and these are the brightest ones here, but there's observations about 30 to 40 days after peak, and there's a whole bunch in the middle that you're just missing. And so one thing I did is fit a SALT3 fit, which is used for these type 1A thermonuclear explosions, which is a pretty well understood model. It's a 3-parameter model. And you can, extrapolate out what the light curve could have looked like, but in my sense, I'm augmenting it with data from its analogs, this nearest neighbor analogs. And yeah, you can see that they do roughly track the evolution that we do see, again, with these similar host galaxy environments. And another application you can do is look for missed supernovae. So I was able to find a bunch of supernovae that were never reported when they were initially observed, but they were just sitting there in the data. And in this example, I had one object. I looked for its 8 nearest neighbors, and 3 of them were never previously reported or discovered. 1 was from 2018, and 2 were from 2021, which I was looking, and I ended up reporting these, and I found 84 new supernova candidates with this method, which is pretty great. And you would imagine that you could also use this to find nearest neighbors of rare and interesting things, which of course is not like a perfect science, not that every analog that you look at from a rare object is going to be other rare objects, just because the parameter space is it's very big, and it's very there's a lot of overlap in feature space between objects with different objects with similar kind of feature values. So there is a bit of human, intuition and work that comes into it. But in fact, I looked at a tidal disruption event, found its 8 nearest neighbors, and 2 of them are very likely TD candidates, but we cannot get actual confirmation of them because the events have passed. We can't get follow spectra, but based on their color evolution, the type of host, the location in the host galaxy and everything, we could be a pretty sure bet that these were rare TDs that were missed. I mean, there's only, I don't know, maybe 30, 50 TDs that are like known. So we don't want to be missing them. We want to better our discovery algorithms so that we can improve them going forward. A couple last quick cases before I wrap up this and go on to my thoughts on the transition. One thing that you can do is look for potential supernovae that need to be reclassified. So the first one was a rare subtype of these type 1A supernova called 91BG-like, which is just a small fraction of all type 1A supernovae. And I looked at its 8 nearest neighbors, and I relooked at the classification spectra for all of these 8, if it was available, and 2 of them were actually better. I can argue are better represented by this rare class label that people just either missed or for whatever reason, I'm not really sure. And that was public. And so I'm trying to argue that some of these are better represented by these rare supernova classes. And this is data we already have. This is not going out and getting new spectra. So it's all about maximizing the data set that we do have. And so this is just a broad stroke of all the cool things that we found, some very rare things. Mostly were rare classes, but some of them are supernovae in particular environments, like a younger type 2 supernova, and these and these older evolved elliptical galaxies, which is kind of interesting. And through all of my supernova discovery, the work that comes out of this, I was able to find about and report 325 total transients that were missed, which is about 1% of all the supernova reported for this survey in the time period of that the data was located. And there's no gracious transition besides now that this was kind of my last project for my thesis. So during this time, I was applying to jobs, and here's kind of just like a quick outline, just my story. Everybody's just going to be completely different. But during the summer, I was contacted by some people, some headhunters on LinkedIn, be like, hey, I can set you up with interviews. Do you want to take them? And I was like, yes, I'll take any free interviews, that I can get. And so I took those. Those were great practice, although these quantitative researcher interviews are not exactly like data scientist ones. They were still, very math heavy, very coding heavy. Lots of good chances to practice your behavioral questions and interviews. So nothing came out of that, but it's just great practice for me. And I really hit the ground running in October of just, a couple months ago. And my thought was like, oh, it's a complete numbers game. Let me apply to as many jobs as I humanly can in a day, which it wasn't really a great strategy at all. And I know like people said the job market was very tough. Even like people I reach out to, other data scientists were like, man, I'm glad I'm not, applying right now. It's been tough, but I think I definitely did myself a disservice by doing that and not like optimizing my resume for the job ad as much as I should have. And the best way truly, as previous talkers had said, to getting referrals is the best way to get interviews. My response rate was about like 1%, which is pretty bad. But it's also like maybe not too much less than average. And I know that it would have been nice to have seen this kind of thing last year before I started applying. And then I quickly transition over and say, okay, well, let me tune my cover letter and my resume seriously and really like look through the keywords in both. And I don't know how true it is, but here, if you kind of need to have like a high percent match rate between the job ad and your resume for your resume to get past a lot of these automated like recruiter screenings so that a human actually looks at your resume and can give you a potential callback. And then, well, I guess it's a little bit cut off with the formatting now, but I had a couple first round interviews for data scientist roles, a couple second round interviews, one of which was on site, and I just got my first job offer for a senior data scientist role 3 days ago. So I'm like, thank you. So, and I think I'll leave this up, some thoughts here, and happy to answer any questions because I know my time is limited. But yeah, I'm just going through the process, and I'm sure a lot of you are too. So I'm happy to answer any questions and give my thoughts on anything. So thank you.
I have time for a quick question or two. Online, anyone?
Well, I'll throw one. So I would say that the two ways to cheat the algorithm when you're applying for jobs, one is, like you said, the referrals, and the other one is, like you said, tailor your resume to the job ad. I don't know how many jobs you apply for or whatever, but which one of the two would you say had a better rate?
Let's go back. Probably technically the referrals. And I didn't even like utilize all of them. I was expecting this process to take a little bit longer, and I was gonna kind of parse out the referrals. So I always kind of had ones coming in. So and out of 5 referrals, one led to an interview, and actually like one of the companies I was interviewing with told me in the recruiter call, like, hey, I heard you got referred to by this person at the company. We really like him. We trust his word. We're gonna heavily weight that in our decision. So they were very frank about that, and that was very useful. The tailoring application, I sent out 28 after I did this. 17 were no responses, but the job offer that I did get came from this pool of 28. And it was kind of right after I made this change. Was that first interview come on? So I think they're both effective. Definitely, probably the referrals. And then in doing that, like I was even reaching out to people on LinkedIn that I knew had like an astronomy PhD, but from another university that had a mutual connection with some other person from my past, and just reach out, just in like a nice measure to be like, hey, I saw you made the switch from astronomy to data science, and saw you have a connection with this person. Would love to just like pick your brain for 5 minutes. Can I send like a question or two? And they're usually pretty nice and be like, yeah, of course, totally. And I've had a couple of people even be nice and be like, let's Zoom for an hour, like let's talk about how I made the transition, and all of that really, really helped. So yeah, it's a little scary and daunting to just like kind of blindly reach out. But it's kind of what you got to do. And I would highly encourage that you do it.
Speaker again. Thank you. Yeah, do you want to switch to her? All right, so our next speaker is an extremely distinguished and amazing person who also happens to be my manager and boss, Julie Hollek, who is the Director of Data Science at Mozilla. And she's going to talk to us something that is near and dear to my heart and hers as well, on building a fundamentally grounded key metric.
Hello, oh, screen sharing. Are we seeing my slides?
Yes.
Okay. And can you hear me?
Yes, we hear you in the room.
Awesome. Okay, cool. Yeah, so as Jeff said, I'm Julie. I am the Director of Data Science at Mozilla, and I'm here to talk about metrics. So quick agenda. There is no astronomer turned data science talk without a quick background on how I got here. I want to talk about metrics, like in general at a high level, and then I want to walk through a case study around MAU, or monthly active users, which is a really common metric that you see in industry. But before we get started, this talk was built on conversations and documents that were created not only by me, but like representing my entire team, both data science and data engineering at Mozilla. And so I would not have been able to make this talk without these folks and then many others who are not on the screen. So again, what is a data science talk? Without a little bit of background on how I got here. So I graduated from the University of Texas at Austin, where I studied the chemical composition of metal poor halo stars. And the thing to note about metal poor halo stars is that they are very old. Right after grad school, I did a coding boot camp. And so I had a 12-week stint where I was convinced I would be a Python web developer. But I ended up getting a job, ironically, at a company called Newstar as a data scientist. And at Newstar, I worked on ad tech. And I think like ad tech gets a bad rap for a lot of very legitimate reasons. But I think something to like always keep in mind is ad tech is what has funded the development of the internet really to what it is today. And ad tech has lots of money to throw at big problems. And so there's a lot of innovation that happens in ad tech. And so one of the biggest areas that I worked on when I was at Newstar is this field called entity resolution. And it's trying to take disparate pieces of information and figuring out like what person or business or entity like those pieces of information really belong to. And this is sort of thematic throughout my career in ways that I did not expect when I got my first job fresh out of grad school. After Newstar, I made my way to Twitter, where I worked in trust and safety. And a lot of the work that I did in trust and safety relied on entity resolution because bad people would do terrible things on the internet and then they would come back after we told them to go away. And so trying to figure out like signals of like who these people were and when they kept coming back was like increasingly important. The other thing that I think is really interesting about trust and safety is that there are quite a few astronomers and physicists that make their way into trust and safety data science. I know like a lot of folks, and then I know like friends of friends who have made their way into it. And I think it's like I have hypotheses as to like why this is so, but that is a different talk, and I am not that kind of doctor. After Twitter, I made my way to Mozilla and I worked on a whole bunch of different things. I worked on revenue, I worked on subscriptions, I worked on metrics. I even did a quick stint doing trust and safety for social media. And now I'm the director of data science. And my experience as director of data science is really the inspiration for this particular talk. And a lot of it is because of metrics. So I want to make a brief case for metrics. So like there are a lot of really fascinating new technologies, right? People talk about generative AI and like LLMs and like neural nets and like whatever, and those are great. They're going to revolutionize like how, or at least they have the potential to revolutionize like a lot of like modern society, right? But I want to make a case for metrics. Simpler techniques, and by that I mean like counting stuff, because I think that they're really powerful. Metrics like frame how your company views its product and how it views, let's say, its customer experiences, depending on the kind of product that you have. And it also is like kind of like the fodder for making decisions, right? And so like being able to do something as simple as counting well is like really important, and it helps your company like have a narrative. And so like metrics, even though they're like, let's say, less on the surface interesting than these like new fancy technologies or something, that I think really deserve care and attention. So the name of this talk is maybe a little bit silly. And in the spirit of astronomy, I definitely came up with the acronym before I came up with the words behind it. But like the words behind it do mean something. So what do they actually mean? Let's break it down into its component parts. So fundamental in this means like all of the pieces needed to make measurements. So like when you're thinking about metrics, what are the building blocks, right? Think things like probes, and then like the resultant like data extraction that you need to get to like some sort of like set of information like that you can eventually query, like the manipulations that you do on top of it. Those fundamentals are like really important when it comes to metrics, especially when you want to do them well. What does grounded mean? Grounded here means like the checks that the systems are working, that like all of these different pieces of the measurement are things that kind of check out. So like in astronomy, like we discussed earlier, we have like biases and flat fields, and those are like nice to kind of set expectations for yourself on like what reality is. It's harder to do that in data science, I think, sometimes, because there is no physics that you're trying to get to. It's just sort of seeing like what things are going on. But you can do all sorts of different types of things to try to make your system more transparent and documented, so you can sort of follow what's going on to try to understand the different parts of your system to make sure that things are working the way that you expect. And finally, key metrics. So like, I think maybe the most obvious example of what a key metric is a KPI, key performance indicators. Companies often use them, and they're attached to bonuses and all sorts of other like things, like what is like the quote unquote North Star metric of a company, how is it doing, right? But like, I think you can also think of like key metrics as being like just really important metrics that you need to like get right, right? So I think a kind of caveat to all of this is that measurement is a craft. And by craft, I mean it's an activity that involves skill. And you can improve on the craft of measurement through different like methodologies or like more instrumentation or whatever. But like deciding how to proceed with a measurement, that is art. And what I mean by that is that like not every single thing that you produce that has numbers has to have the same kind of care and attention. And honestly, I think that this is like one of the hardest lessons to learn as like a newly minted data scientist. Like what are the situations where it's like you can kind of just do a back of the envelope calculation and then be done with it, versus what are the things that like merit a high level of attention. So like thus far, I've been talking about metrics in a pretty abstract way, but to ground ourselves in a more realistic example, let's talk about MAU or MAU, some people call it, or monthly active users. So what is this? This is a metric that is like very common in consumer products, and it demonstrates, it's like the user footprint, like how many users like a product typically has. For something like a browser or a website or an application. Like you can kind of think of like, you know, some apps maybe you use like once a week or once a month. You don't always necessarily use them like once a day, but like once a month is kind of a thing that like a lot of companies, including companies like Facebook historically and like Twitter, have like looked at as an indicator of like their performance. And yeah, it's like very common across industry. And so since it's so common, it should be really easy to kind of understand everywhere, right? That would be actually incorrect. The first issue that you run into is monthly. How long is a month in days? You can do a whole bunch of different silly things like summary statistics to try to figure this out, right? You could take the mean, right? I've been telling my daughter, my older daughter, that this is her year because this is the year of the dragon. And also she has a birthday, which is unique because she was born on leap day, which means that this year there are 29 days in February, right? So you can't even like year over year be consistent necessarily, because like leap day gets you once every 4 years, right? You can take a median that's 31 days, but then you have a bunch of months that don't have 31 days. Same thing with a mode. you can go by like the calendar, like maybe a month has exactly as many days as it needs to, or you could standardize it. And really the issue is that there is no right answer, and it really depends on your business. And I think the other thing, the hard lesson to learn in data science, unlike science, is that the answer to like what should I do in this situation is like almost always it depends, right? And it depends on the context of your data, of the business. And in this way, it's like month is just like, it's like time, right? Like why does this like so specific, but it often is. Active is the next big question. What counts as active, right? You might have some intention of like activity that like you want your users to take, but users are people, and people are wily, and they don't always do what you expect. And so like, what are the different types of activities that like users could engage in, I think is important to like understand. And so in order to get there, you have to do exploratory data analysis and look to see like the different things that you might expect users to do. Do they do them? Are these signals like valuable? And then like the other kind of question is like, how do you retrieve the signal of activity? It might be that you have an application and the point of it is to make people so delighted that they like click on a button every single day. But like, and the thing that you want to get to is delight, but there's no activity that is directly related to delight. Like you have to like kind of triangulate around and treat it as like sort of this like mysterious thing that you're trying to proxy, right? And so like you have to do the work here to sort of figure out what signals make sense. And then finally, users. And in some ways, this is like extremely challenging. Who or what counts as a user, and do you have a login? Let's say you do have a login, which is great. So like the users log in. So then you can maybe just like look at the number of users that like log in every day. But what granularity of users do you care about comes up? Like on some apps or websites or like whatever, you could have multiple accounts. Do you count as one person, or do you count as the number of accounts that you have? Again, it depends on the application and like the use case. In some companies that are public have to like talk about their user counts, and like fraudulent or spammy user accounts like are kind of challenging, right? Like there are users, they show up in like your metric system as like users, but like they're not real, right? So then like, how do you do spam detection and removal, right? And then that's just like assuming the happiest path where you have a meaningful login. But what if you didn't, right? What then constitutes a user? What is like usage? How do you get over these like kind of fraudulent things, right? All these different like points to consider, I think, are really tricky. And so something that is like industry standard is MAU or MAU is like a lot more complicated, and it makes counting so much harder than it seems like it should be on the surface. So like, let's say you've done your exploratory data analysis now, and you've decided for your use case, you have monthly active and users, and you know how to combine those concepts together into something useful for your end goal. And that's great, right? Now, is it the time for you to present this to your CEO? No, it absolutely is not. There are few work scenarios more painful than baking some handcrafted artisanal SQL the night before a board meeting so your CFO can report the numbers to the board of directors. Ask me how I know this. You need a system. Oh, oops, wrong slide. So at this point, you know, like we have this thing that's kind of baked, right? Like we sort of believe in it, right? So we've done like a lot of ideation around like we have this like need to like count our users, have a usage metric. We've done the work to figure out what monthly active users are and how to combine them. So we've done like ideation and development work around this. And like the next step is to like really get people on board with this, because the thing that's like always tricky is that like what a user is to you might be different to somebody else in the same company. And like definitions that are separate in everyone's heart and different are not great definitions, right? And so the next step is review. Are we confident in what and how we're calculating this metric? If the answers to these questions are yes, then we need to start to socialize this and get stakeholders and other people in our company on board. And this means that they are in a position to agree that this metric is what they need it to be, as well as how to like understand and interpret it. And something to note is that like this room is filled with technical people. Like literally my room in here, but also this room in Louisiana. And a lot of your stakeholders will not be particularly technical, actually. And so communication to a like wide variety of audiences is a key component of metric development. And so like, what does this kind of communication look like? I think it depends, again, but things that I think are pretty like table stakes in my mind in terms of like, especially like a high level metric, is you need some sort of like visualization. You need to be able to like show people like what it is, how it moves, what it looks like, because it's not real until you do that. And then the other thing that you need is you need enough documentation to have like a solidified metric definition where you can like point to people and say like, this is what this thing is in a real way. And then once you kind of have these pieces together, you can get sign off. And once you get sign off, then it's like it's really go time. And now this is where the system is really built. Like we talked a lot about like kind of like the socialization and like sort of the philosophy behind a metric, but like now we're at the point where it's like these are solid and we feel good about it. So it's time to build like the technical underpinnings. And the technical underpinnings of this metric should be ones that are stable, which means they need to be well vetted, automated, and monitored. So during the ideation and development stage, you're likely building out like ad hoc work streams to do your EDA and to really start to shape your final proposal for your metric. This is like a totally normal process in data science, right? People do lots of silly things in notebooks, which is great, and you should be able to do that in the ideation phase. But now is really the time to start to formalize this into like a productionized system. And what this means is that the code surrounding the signals and their extraction that are incorporated into the metric need to be code reviewed, and they need to be tested. And they need to be like documented well. Often there are multiple signals that get incorporated in determining like high level metrics like MAU. Like maybe there are different activity signals that are equivalent, or different definitions of usage that like make somebody a user. And those data sources come from different places. Each of the steps involved in the processing of these signals need to have the same level of rigor applied with code review and tests, and also alerting. While the goal of having a system, right, is to just work, right? And so then you can take that effort that like would be put into, you know, getting all the data into interpreting what's going on with the metric. It's kind of unrealistic to assume that the system will work flawlessly. And therefore the system should be well documented and traceable. And speaking of documentation, for critical metrics like corporate KPIs, they really do need robust documentation at multiple levels that go beyond just the technical specs. And in many cases, the non-technical documentation is even more important, providing expectations for what the metric tends to look like, or different, let's say like cuts of the metric, like sometimes like you might like want to like do cuts by country or operating systems or like whatever. Being able to like show that and explain it to people is like really important. I think the other thing too is like, working with stakeholders in an ongoing basis to interpret and understanding the meaning of the metric's values and its evolution over time is like really important with these kinds of high level metrics. And again, this is like another place where communication here is like really key. Like a lot of the job of a data scientist, I think, is education and continuing education, because these things are very fluid. So now you have like a bona fide metric. It's been explored, reviewed, productionized, tested. Awesome, right? You have alerts. It's been documented to within an inch of its life cycle. What's next? It's like the maintenance phase. And at this point, the metric has reached some level of maturation. And then maybe something also to point out is that this can be a difficult stage to get to, but like, let's dream big here, right? So you can do things like having alerting, not only on the processes that go into creating the metric, but also on the metric itself. Like you'll have it'll be mature enough where you can kind of understand what its patterns look like over time. And when things look extremely weird, you can kind of like have a signal that goes off. For metrics like MAU, these often come with forecasts, and the forecast can be leveraged for this kind of insight. There's a program manager who works on the mobile app, and he always notices when something is weird. And a goal that we have is like, can we get to a weird data anomaly before this particular program manager? And that is like a really good measured success. Yeah, so I think the other thing to kind of know is sort of like, yeah, like related to this program manager, metrics and data related incidents always happen. Like nothing is perfect, right? Sometimes these are a blip on the radar and they require a backfill, and it's like, fine, it's not a big deal. And sometimes they mean that the metric is actually incalculable for some period of time. There, like, you know, there's like a data outage, or like a probe gets unregistered, or something happens, right? And this kind of interruption can mean changes to the metric calculation itself, but at the very least, this needs to go into the documentation to like, so people understand like what's going on. And likely these kinds of incidents require clear communication, especially when they impact something like MAU, especially up to the executive level. And so then maybe one like kind of last thing to call out is that like, we stuck to like kind of the domain of data science, analytics, engineering, data engineering in this like life cycle of a metric. But depending on the nature and sensitivity of your metric in your industry, like there are other considerations around security, IT, and data governance that like might be things to think about when you're thinking about these high level metrics. And so like takeaways, I can just leave up on the screen. I don't know, metrics are great. You need a system, documentation and communication are both really important things. Thanks.
You can take a couple of questions, but midday, right?
If there are no questions in the room, I have one.
You got one in the room.
There are? There are not? Okay.
One in the room, yeah.
Thank you so much for this talk, Julie. I loved it because part of the reason is I was in charge of metrics in my previous job in the industry. It is a painful thing to do. What I wanted to say is kind of, if you agree with that, the astronomers have a background that will let you do a number of things very well. Communicate in a technical manner, communicate in a, you know, street level manner, the same concept as needed. You know, you can do the technical, you can do the street level. Documentation, we are very good at documenting things. So all of these type of things that an astronomer will have are super useful for a data team that is dealing with this type of stuff. I don't know if you agree with that, but I think it's one of
definitely. One of the things that I like to say to like grad students like that are thinking about making the jump is like, especially like for observational astronomy, like you go out and you take what the night sky gives you and then you mine that data for physics. In industry, you like do kind of the same thing, but like you mine that data for profit, I guess. But a lot of the techniques are very similar. And I think like even stuff like grant proposal writing and stuff like that, like is very good to like kind of prepare you for these types of activities. And I think some of it is just like having a like translation layer between like, this is what you did in grad school and this is how it translates to industry is important. So networking and talking to other people who've made the transition, I think it's like really helpful.
Julie, thank you so much for that talk. I was taking copious notes, and I hope you'll consider writing a blog about this sometime. Where do you see failures the most? You sort of made reference to this, but I was wondering if you could kind of take us through the places where things break down.
All over the place. Jeff is probably the most intimately familiar with some recent ones.
Okay, yeah, I need to repeat the question, sorry. So yeah. Yeah, sorry. So just I forgot the question. Yeah.
Oh, where do I see failures?
Oh yeah, what are the failure modes?
Yeah. So like sometimes it's like just like the ETL processes, like a lot of these things are sort of like precariously like daisy chained together. And if like a failure happens upstream, then like downstream nothing happens at the end, right? That can sometimes be like a big problem. Another thing that I sometimes seen is like, you know, it's like technical systems look like they failed, but like actually often it's like human error, right? Somebody's like merged something that like did something weird and it has downstream implications, or someone forgot to renew the probe and then the probe is no longer collecting data, those kinds of things. But that's why like documentation and then like making things traceable, I think is like really deeply important. COVID really messed up a lot of things, including data, right? And a lot of like the trends that you were like looking at over time totally did a reversal. And so like there's sometimes these like black swan events that occur too, where it's like you have to sort of like take a big step back and sort of like reorient yourself to try to understand what your expectations are going forward.
Okay, thank you again, Julie.